Okay, so a chemical reaction. Can someone describe to me a chemical reaction first? What has to happen in a chemical reaction? Very good. You end up with something different, okay? A chemical reaction is when a process or one or more substances get changed into one or more different substances. Okay, that's the basic definition of a chemical reaction. Okay, we're going to look at chemical reactions and how we set them up into chemical equations. But essentially a chemical reaction means a change has to take place. So if ice melts from ice to water, is that a chemical reaction? No. No, right? That's a physical change. So we're not changing the identity of the substance. That's when a chemical reaction has taken place. Okay? Substances, it's changed into one or more different substances. Okay, chemical reactions or chemical equations are made up of two distinct parts, kind of the before and the after. Do you know what those two things are called? Reactants and products. Good. Reactants are what we use to make our products, right? So reactants come on the left or the right side of a chemical reaction. Do you remember? The left, right? These are what we start with. Okay, so the reactants are what we start with. It's what does the reacting, and the products are what is made. Okay, so the reactants are what's doing the reacting. The products are what has been made or what's been formed. So if we have a very general chemical equation here, what's the arrow sign mean? Do you know? What does the arrow mean?
It means like it's showing the reaction.
Yeah, it means the reactions take place, or this means yields, right? It produces. So A plus B added together to give us C and D. So out of these four things, which are our reactants? A and B. So this side is the reactants. Anything on the left side of the arrow are the reactants. Anything on the right side of the arrow are the products. Okay? There can be as little as one on each side, but it can't be one on both sides, right? We can't have A turn into B miraculously, right? That's not enough to make a chemical change. It could be A turn into B plus C, or A plus B turns into C, right? But there can't be a 1 and 1. So there's got to be at least three things that are taking part in a chemical reaction. Okay, and we'll see that kind of as we go into the types. But for right now, that's the very general form of a chemical reaction. Products on the right, reactants on the left. Okay. We talked about this just briefly, but what are some indicators to us that a chemical reaction has taken place? A color change, that's a good one. Okay, it releases heat or takes in heat, so we have a change in energy or a change in heat. So this is if we're in a lab type setting, how do we know that a chemical reaction has taken place? And these can be some indicators, right? Some reactions give off both heat and light, both types of energy. But they give off this a spark or a flash or something like that, as well as heat. Okay, both of those are strong indicators that a reaction has taken place. Or some sort of gas has been released, some sort of smell, right? That's an indicator too that a reaction has taken place. So if it gives off a gas, right? Some gases are clear, most are clear. It's hard to see if a gas is being given off. But sometimes if you smell something, right, that means a production of a gas has taken place. That's a good indicator. It could also be when bubbles start forming, right? Bubbles are an indicator of gas molecules trying to escape to the top of a container. So bubbles can form in just, a boiling situation, or if you don't have your reaction taking place on a heated surface, right? If you're not on heat and you see bubbles start forming, that's a really good indicator that a reaction is taking place. Does that make sense? If you're not heating it yourself and you start seeing bubbles form, that's an indicator that we have a reaction going on, right? Because bubbles shouldn't come from nothing. Okay, a solid formed from a chemical reaction is called a precipitate. Okay, so anytime we have some solid that will start to form or fall out of when I say fall out of, means like fall to the bottom, right, sink to the bottom. In a chemical reaction, that's a good indicator that something has taken place. Okay, if a solid appears after 2 or more liquids are mixed, right, it appears from nothing, that's a really good indicator that a chemical reaction has taken place. Okay. We will see that hopefully in a lab that we'll do here. We'll start with liquids and we should hopefully get a solid if everything goes right. Okay. But that's called a precipitate. So when you have a solid that appears from nothing. The last big indicator of a chemical reaction is a color change. Good. If a new color shows after 2 things are mixed, a really good indicator that something has changed. All right. So we can take a chemical reaction and we're going to put it into its quantities or its written form, which is called a chemical equation. And chemical equation is what I showed you earlier. This is the most basic form of a chemical equation. A plus B yields C and D, right? In a chemical equation, we have to put everything that's contributing to that chemical equation. So all of our known substances have to go into that chemical equation. Okay? So all of our products, all of our reactants have to be shown in our chemical equation. Otherwise, it won't balance, right? We have to deal with what we call the law of conservation of mass, and we have to make sure that everything is coming out as it should, which means whatever goes in has to come out. Okay, so things can't appear mysteriously or disappear. Okay. In a chemical equation, we have to have the correct formulas for all of our products and reactants. So we go back to our Chapter 7 naming, right? We have to be able to name compounds correctly. So if you don't know what sulfate is, you're going to have a hard time getting its formula right? So you have to make sure that you're kind of brushing up on those things as we go through this chapter as well, okay? Because I'll ask you to do that throughout the chapter. Okay, so if you have an incorrect formula, it again will cause our chemical equation not to balance, which is a problem. Okay? Okay, this bullet right here says the law of conservation of mass must be satisfied. What does the law of conservation of mass tell us? Yeah, Anna. Good. Mass cannot be created or destroyed. Okay, so created or destroyed means it can't come from nothing and it can't disappear to nothing. Okay, so in our chemical reactions and in our chemical equations, that means whatever goes in has to come out on the other side. It might be in a different form, it might be in a different compound, but it's got to be there. Okay, so we're going to look at counting atoms individually when we solve our balance our chemical reactions. Okay, so atoms are neither created or destroyed during ordinary chemical reactions, and that's what we'll be looking at here. The same number of atoms of each element must appear on both sides or each sides of a chemical equation. Okay. So if I start out with 4 oxygen atoms on the left, how many oxygen atoms do I have to have on the right? 4, right? They could be split 2 and 2 between 2 compounds, could be split 3 and 1, whatever it happens to be, right? It doesn't make a difference how they're distributed, but we got to have equal numbers on both sides. Again, you don't need to write these things down word for word, right? You can start abbreviating things, but in chemical reactions, we have some elements that cannot exist by themselves. They're not stable enough to exist on their own. Okay, so what they do is they exist as a pair with another atom of the same element. Okay, these are called diatomic elements. okay, which means they need to exist as a pair. Okay, they are not stable enough, which means they're very reactive. And if they were to exist by themselves, they would react with too many things, right? They would go pair with whatever they could. So they exist, if we want to look at them by themselves, they have to exist as a pair. And these are called the diatomics. Does anyone know any of the diatomics? Yeah, Alec.
Oxygen, fluorine, hydrogen, nitrogen, possibly chlorine.
Yep, good. Okay. These diatomic molecules, you can look at the list of them on page 263, but essentially what happens in the periodic table is starting with nitrogen and going to fluorine, it kind of makes a 7, right? N, O, F, Cl, Br, and I. Okay, you kind of make that 7, and you add in hydrogen. Those are the diatomics. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, I need to check with the book to make sure I'm right on iodine, but I'm pretty sure that it is. If we say a reaction occurs between hydrogen and oxygen, right, we have to start our reaction like this, H2 plus O2, right? We can't just have H plus O. That doesn't give us what we need to have. So if we say a reaction begins with hydrogen and oxygen, we assume we're talking about hydrogen gas and oxygen gas because they cannot exist in singles. They have to be in pairs, okay? A symbol with just an S in parentheses, that means we're talking about its state, right? And so an S in parentheses would mean that it's a solid, right? An L in parentheses would mean that it's a liquid, okay? A gas would mean that it is, would mean that it's a gaseous state. And an AQ might be a little bit new for you. AQ means that it is aqueous. Okay, and that one is a little bit different because aqueous means that it has been dissolved in water. Okay, so that means that our substance is already in water. So the thing about aqueous solutions is that water is not taking part in the reaction. So water doesn't have any effect on the reaction. It's kind of just the place that the reaction can take place. Does that make sense? It's kind of the environment in which it can take place. So water doesn't affect the reaction in aqueous solutions. It just means that it has been dissolved in water. Okay? A single arrow, like the one shown here, what does that usually mean? Yeah, it yields, or it produces, or it equals, right? Some people say equals. But a single arrow, really, I want you to think of it as yields, right? It produces. Okay, so it indicates a switch from reactants to products. Right? During that time, our reaction has taken place, and now we are dealing with just products. What do you think might be the case with a double arrow, or a double-headed arrow? Any idea? Yeah.
Convert back into each other.
Yeah, good. A double arrow means that we can have a reverse reaction or a reversible reaction. It means it can go forward and then it can go back, right? So then our reactants become our new products, right? And our products become our new reactants. So a two-headed arrow means that it would go forward and backward. We won't get into those a whole lot in our section. Once you start dealing in college chemistry, you might see reversible reactions a little bit more. But that's just something for you to be a heads up about. Okay, so double-headed arrow means that it can go forward and it can go back. Okay? Right, this means that it starts out as a solid, it produces a solid, and it produces a gas. Right, this is the breaking down of this potassium chlorate, okay, into KCl and oxygen gas. Okay, so it would release oxygen gas and it would produce this solid. Okay, we're going to talk about what other things mean, but here the arrow tells us it only goes one way. Okay, you don't really need to have that down. That's just something for us to get as an example. Okay, we're going to talk about what coefficients mean in a chemical reaction. In any math term, what's the coefficient? It's the what? The number in front of the variable. Good. It's the number in front of the variable, and that's the same thing here. Okay, coefficients allow us to represent that we need more than one of that molecule. Okay? So we may need to represent more than one of a molecule to satisfy the law of conservation of mass. So that means in our chemical reaction, if we need more than one of them, we would use a coefficient. We don't alter subscripts in any way. Right? Once we have our chemical formula set, we don't alter subscripts. Right? We just say we need another of that molecule by adding a coefficient in the front. Okay, so if we need 2 water molecules, we don't change it by saying H4O2, right? That's not allowed. We don't alter the substance in any way because this behaves a lot differently than water, right? If we need 2 water molecules, we just say we need 2 H2O. And then when we go to count our atoms, right, how many hydrogen atoms would be represented in this right here? Hydrogen would have 4, right, because there's 2 in each molecule, and there's 2 molecules. How many oxygen atoms would be represented? Just 2. Okay, does that part make sense? We're going to have to be able to count individual atoms, so you need to make sure that this part makes sense to you right here. Okay, the coefficient doubles it just like it would regularly or triples it or whatever. Okay? All right, coefficients also can tell us the number of moles. If we scale it up to think about the number of moles in a reaction, the coefficient not only tells us if we're looking at single molecules, it also tells us the mole ratio, and that's going to be really important as we start moving forward. Okay? So I'm just going to kind of walk through this equation here at the bottom. If you want to write it down, you're welcome to, but I'm going to talk through what it means here. Okay? So the chemical reaction works on 2 scales. We think about the smallest scale. We have 1 atom, or 1 molecule, of C10H8 that combines with 12 molecules of oxygen gas, and it yields 10 molecules of CO2 and 4 molecules of water. Right? But that's a really small scale. That's talking about 1 individual molecule or 4 individual molecules. So when we scale it up, which is what we use much more often, we would say 1 mole, because it doesn't have a coefficient, right? 1 mole of C10H8 plus 12 moles of oxygen would yield us 10 moles of carbon dioxide and 4 moles of water. Okay, so the scale works both on a molecular level and a mole level, which is what we'll work with more often. Does that make sense? So it's all about the ratios of what has to go together to yield our products. Okay? Are we good with that? Give me a yes or a no. Okay, good. Okay, so now we're going to start with our steps for balancing equation, and this is our big takeaway for Chapter 8. Right? We have to be able to balance equations in Chapter 8. Okay? All right, all this stuff at the beginning we don't need to talk about right now. Okay? We started in word form. You need to write the formula first. Okay, we got that. Products go on the right, reactants go on the left. We don't need to talk about all that again. Okay? What I do is balance each atom one at a time. Okay? So we're going to balance each atom one at a time. So we're going to count hydrogen atoms and oxygen atoms and nitrogen atoms or whatever we happen to have. Okay? I don't want you to think about this for right now. Okay? If you have polyatomic ions that appear on both sides, right, if we've got a phosphate on the right and phosphate on the left, you're welcome to balance phosphate as a whole, right? And I'll show you that kind of as we get going. But if phosphate goes from phosphate to phosphorus and oxygen on the right, that you can't balance that as a whole. So that's something I'll kind of point out as we go. It will always work to balance each atom one at a time, okay? But if you can start combining some things to help it make a little quicker, you can do that. Okay. Typically, when we're adjusting our values, and we'll see this as we go, oxygen and hydrogen are going to go last. Okay, so when we're adjusting our values, Typically, we're going to adjust hydrogen and oxygen last. Okay, and this might seem a little bit arbitrary if you don't really know what I'm talking about when I say balance equations. But I'll show you my method, and then we'll point these out again. Okay. The thing about balancing reactions is kind of like Lewis structures, right? But even more so. But balancing reactions only has one correct answer. Okay, so again, it might take you a couple tries to get to your final answer, but there's only one right way to do it. Okay, so it's even more so like that than Lewis structures, right? Because Lewis can have resonance and all that kind of stuff. There's only one correct answer for a balanced equation. So although it might take you a couple tries to get there, you can always check yourself. Okay? Okay. Reaction. Let's look at this reaction down here. H2 plus Cl2 yields HCl. I'll write it a little bit bigger. So right now, this picture is what's going on currently. We have 2 hydrogen atoms, 2 chlorine atoms on our product side, and then on our on our reactant side, and on our product side we have 1 of each. So is that a balanced formula? No. What needs to happen? We need another hydrogen and another chlorine, right, on the right side. So what would we do to our chemical formula to help us do that? Right? We'd add a coefficient of 2. Right? And that would add us another hydrogen and another chlorine. Okay? H2 plus Cl2 yields 2HCl. Right? Pretty simple, right? And with the visual here, it was really easy for us to see. That's not going to happen on every single problem, and I'm not going to recommend that you draw a scale on every single problem. Okay, so I'm going to show you kind of my method for balancing reactions that get a little bit more complex than this one. Okay, but does that make sense? How we have to have the same amount of atoms on both sides. That's our goal. Okay. We don't add coefficients to the middle of a formula ever. Okay, coefficients always go at the front of our formula. Okay, so again, if we have C3H8, right, we don't add a coefficient here in the middle if we just want to get more hydrogens. Right, that's not how it works. The coefficient always goes at the front, and it contributes to the whole compound. Okay. If you're having trouble balancing and you've built your chemical formulas from scratch, that's the first place that you should check, right? If you built your chemical formulas, if you had to write out sodium nitrate or whatever, if you had to write them and your equation is not balancing, checking your chemical formulas is going to be the first place you should look, okay, to make sure that your chemical formulas are balanced. Okay, and then last is that we don't change subscripts in a correct chemical formula. So once we have it established what sodium nitrate is, or lithium sulfate, or whatever it happens to be, once that's established, we don't change our coefficients ever. Okay. That's all a little bit of review of what we've done today. The last bullet here is new. Okay, you can reduce coefficients after the equation is balanced if they're all reducible by the same number. So what that looks like, if I had balanced my equation and maybe I'd overshot it a little bit, right, and my coefficients are 2, 4, 2, and 2, what are those all reducible by? 2, right? So then I would just reduce those down and I'd end up with a 1, a 2, a 1, and a 1, right? And if there's a 1 coefficient, we can leave that off, okay, just like a 1 subscript. Okay, so our final would just really be A plus 2B yields C plus D. Okay, does that make sense? So if you overshoot it, which happens, right, you're just kind of missing something and you double it or whatever, you can reduce it if they all reduce. Okay? All right, let's finally try some.
They can all reduce, or
You have to reduce the whole equation at once. Yeah, you can't just reduce the product side or just the reactant side. Okay, so here's my method. The first thing that you should do is check to make sure your chemical formulas are correct, right? Copper is by itself. It's not a diatomic, so we're good with that, right? Sorry, I'll give you a second to get this written down. My bad. Copper is not a diatomic, so it doesn't need to be Cu2. Silver is a +1. Nitrate is a -1, so that's good right here. They're using copper 2 and silver. So we're good with all of our chemical formulas, okay? Now to balance our equation, this is the method I use. I list all my elements, Cu, Ag, N, and O. And I look at them on both sides. Let me space these out a little bit more, sorry. Okay, and then I draw lines. That way on this side, I'm going to count my reactant side. On this side, I'm going to count my product side. And I want those values to match, right? That's my goal. So I'm going to go through and count how many coppers are on the left. 1, right? And how many coppers are on the right? No, just 1. This 2, remember, only goes to the parentheses. Okay, so we only have 1 copper on the right. Will we agree there?
Yeah.
Okay, how many silvers on the left? 1, and silvers on the right? 1. Okay, how many nitrogens on the left? 1, and how many nitrogens on the right? 2. And then oxygens on the left we have 3, and oxygens on the right we have 6. So we need to go adjust these so that these values match. Okay, so what would be an obvious choice for us to add a coefficient to? AgNO3, right? We need this nitrogen and oxygen to both double. So we add a 2 here, which changes this to a 2 and this to a 6. But what does it also change? It changes silver, Ag, right? So now we have 2 silvers. So now copper matches, nitrogen matches, and oxygen matches. Silver does not. So what do we need to change with silver on the right-hand side? A 2, right? And then I go back here and adjust it. And now I look over one more time. Coppers match, silvers match, nitrogens match, and oxygens match. Okay. This is when I said if you wanted to just look at nitrate, right? If you wanted to balance nitrate by itself, you could say, okay, I have 2 nitrates on this side and only 1 on this side. You could have done it that way too. If you can visualize that or see that your polyatomic ions stay together, that's great. If you'd rather do each individual element, that's great too. Okay, it's however you want to deal with it. Okay, but that's kind of my method, is using this little table. If you can see it, look at it and see it, great. Some people can, some people can't. That's fine. Okay, but this is our final product. 1, 2, 1, 2. Okay. Okay. This means that 1 mole of copper reacts with 2 moles of silver nitrate, and it yields 1 mole of copper nitrate and 2 moles of silver. Okay. All right, let's try the first 2 together, and then we'll look at the last 2 on your own. The states does not have any effect on our balancing. Okay, it's just there for information purposes. Okay, so the solid, liquid, solid doesn't change the way we balance the equation at all. Okay, so how many aluminums on the left? 1. And how many bromines? 2, Br2, right? So there's 2 there. Okay, aluminum's on the right, 2, and bromines, 6. So we need to make bromine have 6 on the right side. So what coefficient should we add? A 3, good, right? We don't add a 6 because it's Br2. So we make this a 3, and then we need to do something to our aluminums. What should we do here? Add a 2. Right, that's it. Simple enough, right? Okay. I will warn you, they do get a little tougher than this. Same process, but sometimes you got to go back and forth several times, and sometimes you just feel a little bit stuck. But second one should be a pretty simple one for us to look at as well, because there's only 2 atoms. Potassium's on the left, I have 1. Bromine's on the left, I have 2. Okay, so to balance my bromine, what should I do here? Add a 2 to what? KBr. Okay, so that makes this 2. Perfect, and then add a 2 right here. That's it. Okay, I will tell you, we do add more than just 2s, right? It might need to be 3s or 4s or 9s or whatever, okay? So you will get a little more difficult. But why don't you try these last 2 on your own? We started this when we had 3 hydrogens on this side and 2 on this side. We can never get this side to be an odd number, right? There would be no way for us to make that an odd number. So the first thing that you should do is start by making this an even number. Get this to an even number somehow. And so the way I did that was that I made this a 2, right? So that way I have 2 hydrogens and 2 hydrogens, and then you go from there. Okay, so if you've got an odd number on one side and an even on the other, you need to start by making that an even, right? So that you can work from there. So that's how I did that. I made this an even first, which adjusted all my other ones, okay? If you have an element that's by itself, I know I said usually you adjust hydrogen or oxygen last, but if you have an element that's by itself, like sodium here, you leave that till the very end, because that's an easy adjustment, as to just to slap a coefficient on that, right? That's the one that you should look at last. Okay, usually hydrogen or oxygen are by themselves, but in this case sodium was by itself. So if you've got one that's by itself like that, that's one you should look at adjusting last. Don't try to match sodium first. Okay, I think that's balanced. So did we agree with that? 2, 2, 2, 1 after we figured it out? Okay.
Oh, so you have to write 1 in there?
No, you don't have to write the 1.
So,
2746.
so why do you choose the numbers that you choose? Like,
I just guess and check. I mean, it's like trying to make it balanced. So, let me see if I'm even balanced right now. I don't know. 2 carbons times 2 is 4. Oh, my carbons aren't balanced. You're right. Shoot. That's no good. Okay, so if I want my carbons to balance, now I've got 4 carbons here. 14 oxygens. So I need that to be a 7. Two, 7, 4, 6. From words to chemical formulas. Okay? From words to chemical formulas now. So you have to write the balanced chemical formula and balance the equation. Okay, so you might want out your periodic table of ions, right, to help you balance your chemical formulas. This guy. Okay. Yep. Okay, so I underlined the reactants in blue and the products in red. Okay, it's just zinc. You don't have to write down the word form in your notes if you want. Just zinc. Is zinc one of our diatomics? It's not a diatomic, so it's just Zn. Okay, plus hydrochloric acid. What's hydrochloric acid? HCl. Good. Okay, it forms zinc chloride. So we need to put together zinc chloride. Zinc is a +2 or a +1? It's a +2, and chloride is a -1. So our final product would be, or our final formula would be ZnCl2, right? And then hydrogen gas, which has to be H2. Okay, do we see where those formulas came from? It might have gone a little bit faster than you're ready for, but zinc chloride comes from, we know zinc chloride together is an ionic compound. It has to balance, right? So if it's +2 and a -1, we can cross those down. Because this was ZnCl2.
And then how did you get hydrogen as 2?
Hydrogen gas, so since it's our diatomic, it has to be 2 of them. Yep, it's got to be the pair.
How do you know?
So it's just that list of ones we memorized. Hydrogen plus this, okay, plus the 7 or whatever. Okay.
What did you say? Where did you get the H2?
This is a diatomic, so it has to exist as a pair. Those are the lists we went over earlier.
Oh. I will do this one.
Why does there have to be extra? I'm not stopping till I finish this. I'm figuring this out.
See, I give you an easy one after a hard one.
Thanks.
Throwing you a bone.
Bit better about
See, it's not that hard.
No.
Okay, is this what we all had? Okay. Try this one on your own. It's very similar to the one we just did. Actually, I don't want you to do that one. It's too close to the one we just did. Sorry. It's like almost exactly like the one we just did. Blah. Okay, here we go. Nitric acid reacts with magnesium hydroxide to form magnesium nitrate and water.
Yes.
Nitric acid, yep, comes from nitrate, HNO3. Yep.
2, 7, 4, 6.
If you want me to check your formulas before you start balancing, I can do that. Raise your hand.
Because that's the one that's about. Yeah. Because O and H. Yeah, because there's two oxygens that line of fire.